The next activity, which is on, I don't know, 2 pages further, is a caldera in a box. And this actually is, so one, I've never done this before. So I'll just let you guys know that. Science in action. And, you know, we can all learn together. 2, what we saw in the, what was the last video where we saw this deflation event, was really cool. And we're gonna do this again, but to where we can actually control it a little bit more and look at kind of faulting that happens around inflation and deflation. In theory, you could do this and inflate a body of material, a magma body, but I think you might just get covered in flour. So we can save that for my baking skills. But for this adventure, you have your small cardboard box, which used to say Caldera in a box. I've cut all those wings off to hopefully allow us to see in. You cut a small hole in the bottom, and then you line it with some newspaper to hopefully minimize the amount of flour on your desk. And the reason why we want to use flour is because it is ground so fine that it actually starts to clump together. And you probably all notice this as you've, you know, cooked or baked with something. Flour kind of likes to pack and form these blocks. It has to do with its grain size, which is really nice for holding up weak structures like these faults that we're going to create. We also have some plastic tubing. This plastic tubing, I've noticed, is a little bit stiffer to where the bulldog clips don't actually close it off completely. And so I found a workaround for it. We also have our balloon, which is our magma chamber. So we'll put our balloon on. Cynthia's given us a number of rubber bands. And we're actually going to just do a little lark's head on here, which is just kind of loop it through itself. Maybe do that a couple times. And then we'll put the bulldog clip on that, and that actually is going to hold your balloon in place. And so, good to go. We can inflate our balloon. So our magma system has gases to the base. The next thing is that you have a tiny little pipette, and I don't recall what the original purpose was, if it was to fill it up. It's actually a really great stopper. So the next thing you'll need to do is blow your balloon up, cover it, and then put the stopper in. And so then we have all of it held. And then we'll feed it through the stopper side, through that hole. Got to make sure your hole is big enough to where your balloon will fit into your box. And then you'll have to, the nice thing is the stopper is tapered, so we can actually let the stopper out just a little bit. And we can deflate our balloon some. You might have to, yeah, and you might have to like turn your volcano just a little bit. Because that bulldog clip is a little bit bigger. What if we do
on the outside of the box?
That's what I'm going for. Good call. That gonna work. Okay. Try number 3. Feed your balloon through the bottom of the box and then attach it. So,
I think it's really important for students to see when the demonstrations don't work right, because that's what science is. It's never, oh, we just follow exactly this recipe and it's going to turn out. No, it doesn't. But that's the fun part too.
Yeah, it's good to have a little bit of trial and error on these things, because I thought I was really clever with the bulldog clip, and then that's failed a little bit. Okay, so we're back there. Let's see if we can blow this guy up again. Okay, so we got way too big of a volcano at this point. We'll let some air out. Okay, we'll do that. No, that seems like a lot too. Okay. And then, that actually still seems like a lot. Okay. So smaller balloons might be easier. But, so we got our balloon in here, and then we'll start to pack in flour to create our favorite volcano. Does anybody have a favorite volcano? Hands raised, nothing.
Dante's Peak.
Dante's Peak, woo! Says it's in Washington, but that was actually filmed in Wallace, Idaho.
Oh no!
I have a love-hate relationship with Wallace, Idaho. So we'll slowly bury it, if you can see, in our material. So we have a little bit of an offset chamber. So this could be a little bit more like Mount St. Helens with our offset possible collapse that might happen. But we'll keep packing it in. My favorite volcano is actually Mount Baker in Washington, which is not because we're using Baker's flour. Let's see where we're at. We'll just do a little bit more flour. So it looks like we're using about 3 cups of flour. I think you could use more or less. Depends on how big your box is. Okay. So we got a volcano. Dante's Peak was pretty tall. Just close that a little bit. It's winter because it's covered in snow, right? So we got our little volcano. And what we can do is, so we don't see any sort of structures, it's obscured, and we're gonna pull the plug. So right there, and we'll do it slowly. You guys see it starting to collapse. So it would have been better, and I can't see this, so please tell me if I should go left or right. But we can actually start to, huh?
Down.
Like tilt it down.
Hold on one second. I have a second screen. Let me just move this over, and then I can actually watch what I'm doing.
Really? You want to watch what you're doing?
So we have another question. So other than the mess, is there a reason not to do this with layers of sand, flour, and chalk dust, or just pop the chamber? Outside, of course. That was a question.
You just won't have, there we go. We can try this again. So you can start to see these fractures along here. Nice nail, Nels. And So, and actually maybe we'll turn the box. So we can see some of the deflation faults. And what if we fill this back up and try to watch it from this top down? Would that make sense? This could be bad. Pull the balloon back. Okay, our balloon's back. Sorry. Let's add some more flour. We'll change it up. We'll go for a Caldera versus a stratovolcano and see if we get slightly better result. Right. An okay angle. Yeah. So we'll drain the magma chamber. Slowly, maybe. So we had a side collapse. So just a tiny, man, there we go. Just a tiny collapse on one of the sides. So this would probably be nicer in a much bigger box. And so we can actually start to look at, tilt this maybe. So we can even see, it's hard to do this. I apologize. So you can actually see little fractures that are starting to form along the edge as it would slump in, which is pretty common of these ring fractures.
It's interesting to notice the dip on it as well.
Yeah, my balloon was at a bit of an angle. Now we're having catastrophic failure of our Caldera system. But yeah, the balloon was not flat. So it was at an angle like this. And so you could actually, it's more of a trapdoor style Caldera versus just a cylinder dropping straight down. So even Calderas themselves are unique. And you know, they're even over time, they'll slowly start to fill themselves in. But you can actually start to see some of these blocks. This is mostly from me moving it. But yeah, so there's a Caldera in a box. A little bit more difficult.
Does anyone have any questions?
I have a question or just a comment. So for me, from my level of tremendous ignorance, I'm just trying to grasp what is this modeling. And so I think, Nels, you have in mind all of the different events in volcanoes that you are comparing to or looking for models of. And for me, I don't have that, and I have to assume that the students, at least at the elementary level, don't have that background knowledge either. So yeah, what background knowledge should I be giving to students if they're going to try to make this model or observe it?
Sherry, would you pull back up your presentation of the Caldera system through, if possible, and we'll try to walk through this. Because that's a good question. Yeah, I apologize that there's in one of the first presentations on the volcano in a cup, having that real world conception right next to the model that we were creating is probably most helpful. So that's a great observation. We'll see if we can get Sherry's presentation up. Yeah, I think if you go to number 8. So what?
I'm sorry,
go
you guys have this in your notebook, by the way. If you go to section, I'm sorry to interrupt there, Nels. If you go to section 6, there's a picture of a volcano. Looks kind of like this, and then the next picture over is the collapsing caldera. So sorry to interrupt.
No, that's great. So yeah, on the right-hand side of this image, you know, what we're creating to start with is, you know, we're just the start of the volcanic edifice. So there's magma in the earth, and it's buried under, you know, a bunch of rocks and layers and whatnot. And what's happening is, as degassing is occurring, or you might have some smaller eruption occurring, you actually start to have the rock overburden starting to collapse into the caldera itself, so into the magma chamber. And eventually, when you have enough of that occurring, you can have eruptions at the edges or in the center. And then after that, you can have leaking out of magma later on, similar composition, and you know, typically a lot less volatiles. And so if Sherry goes to the next slide, where we can actually see the caldera itself, the outline of the caldera of the Valles caldera. And so all of those domes that are forming on the northern margin are this little bits of magma that's or lava that's squeezing up after the fact. And that's where the obsidian is in the Valles.
So this is where the approximate position of the ring fractures here, right here.
And in the case of the Valles, it was more like the first example that our volcano or caldera in a box was, where you just kind of had an individual down drop block. And so more like a piston in an engine going up and down. So it just kind of slides down as material is being removed from inside of the caldera system. Where in the second one, it was actually a little bit more of a trap door. So think of just part of it swinging down because of the angle of the magma chamber itself. So part of it lost material faster than other parts.
And in the case of the Valles caldera, using geophysical techniques, we know that the Valles caldera is a little bit of a trap door. It's deeper, thicker. The caldera fill is thicker on this side of the caldera compared to this side.
We had another question. In nature, does the material above the magma change or relate to the type of collapse?
Well,
I would say yes and no. Part of probably what may be occurring, and Sherry could definitely say this more, is that, you know, in this volcanic system in the Jemez, you know, we have layers of harder volcanic material and layers of softer volcanic material. And so oftentimes those boundaries between the two is where fractures occur. And you know, when you have those different compositions of and strength of rocks, that's in some ways that's going to dictate how these things are going to collapse. And so I think if you had even layers of sand, flour, and chalk dust, they would probably fall along, you know, it might be more symmetrical in how it fails, because you just have even layers. If you had things interfingering a little bit with each other, then those would be the boundaries where it would likely fail. So it could potentially behave more like a piston rather than a trapdoor. But it also depends, you know, on the shape of your magma chamber as well. So if you had a perfectly, you know, spherical balloon, you would probably have some sort of a bullseye target. If it's offset or at an incline, you could have more of a trapdoor. So those are things to think about, is, you know, the shape of your chamber is going to affect how it's going to collapse. And I think that's what Lorraine just asked.
Yeah. And in the case of the bias caldera, the caldera actually erupted through the western edge of a rift basin. So there was already some asymmetry going on, and it certainly wasn't enhanced by the caldera collapse.
So I think looking at Fred's comment, which has to do with the different layers, that would actually be a cool experiment anyway if you popped it, because not only would you have collapse, you would also have the eruption. So you probably would have parts of the stuff being ejected out, but then you would actually see these blocks falling back in, maybe not as cohesive as you would like, but that could be interesting. So I don't know if Sherry knows more on that, but Tamara had a question that is, do we know any recordings of traditional stories of this area, and do they correlate with the actual geology and volcanology? I think all of these eruptions are too old.
Yes,
for human observation, but I imagine names of places by the Pueblo and the probably do come into some stuff. I know, you know, if you go to Sunset Crater in Arizona, which is the youngest eruption, 600 years old.
Yeah, and people saw it.
Yeah. And there's even spots where you could see Native Americans cooking corn. There's like corn indentations on some of the lava flows. So there are places that definitely have that. And in Hawaii, you know, all of the names are Native. And the Hawaiians had a really, I don't know if intimate is the right term, relationship with Madame Pele and worshipped her because of her giving and taking, her wrath when she would just, you know, run over her village with a lava flow. So she was not one to be trifled with.
So there's another question. In the caldera this morning before break, you indicated magma is contained within. So we have a projected shape of chamber of magma. Is that, I guess that's a question, sort of. So is there a projected shape?
I would say, well, We often try to model things as simply as possible. And so we like to think of these magma chambers as spheres. We do know that is 100% not the case. And if you look at geologic models, oftentimes they start at a sphere and then try to complicate it as much as possible to reflect what they see on the ground. So there's a lot of different ways to model a spherical point source. And then that way, then you're only dealing with, rings going outward. But in the case of, the Socorro magma body, it's an elongated ellipse, and probably not very thick. 50 meters, 500 meters, I can't remember.
Yeah, it's less than 100 meters, and
Yeah.
it's basically a pancake. It's a sill.
Yeah, a bad, flat, elongated pancake.